Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Assett. I want to discuss with you the very interesting study that just came out 4 months ago or so. You see the published date there, March 22nd of this year. It's in the Drivers of Interannual Sea Ice Concentration Variability in the Atlantic Water Inflow Region north of Svalbard. Okay. Now, this is a very lengthy article, and it gets very detailed. I'm not going to go through this in the detail because I'd be yammering away for about 3 hours here. What I will do is I will leave the URL link in the comments section. So I'll post a video, and then I'll put the URL in the comments section. So you can go into the comments section, look for my comment there, click on the URL, and you can then read this in and study this in great detail. There's a lot of information packed in here, but there's some things I want to point out to you. So here we go. Abstract. Okay, sea ice concentration along the continental margin of the Arctic Ocean is influenced by a multitude of factors, including local freezing and melting due to atmospheric forcing, lateral advection of sea ice by winds and ocean currents, melting from below by warm Atlantic water, abbreviated AW. Here we characterize the evolution of sea ice concentration in an area on the continental shelf break north of Svalbard. What we mean by the continental shelf break is where the shelf then starts dipping down, getting steeper as you head towards, in this case, I think it's the Eurasian basin. But it heads down into deeper depth. So it's like you have the shelf, then the slope going down to deeper layers. That's what they're talking about there, the shelf break, where it starts getting deeper. And they looked at the period between 2012 and 2019. During this period, a semi-regular seasonal pattern in sea ice concentration was interrupted by 3 anomalous seasons: a high ice anomaly during the autumn of 2014, a low ice anomalies during the spring of 2016 and 2018. Neither type of anomaly can be explained by abnormal upper ocean heat content as measured by ocean mooring located near the shelf break. Okay, this is what they're finding a study. Now, a lot depends, okay, where you place the mooring. Perhaps they didn't quite place them in the right spot to actually, really measure what the ocean heat content was doing. That's a possibility. So what they found was that the predominant driver of interannual sea ice concentration variability during this period was variation in large-scale ice drift. While heat flux from the ocean cannot explain the interannual variability, according to this study, it plays a key role in maintaining periods of open water in the AW inflow, Atlantic water inflow region, despite freezing air temperatures during most of the year. Well, remember the specific heat content of water. These results are consistent with the sea ice concentration flux divergence from satellite records, which suggest that the southern continental slope of the Eurasian basin, I was right, is an important melting area for sea ice advected in from the north. Let me repeat that. The continental slope of the Eurasian basin is an important melting area for sea ice advected in from the north. Now, the sea ice comes in from latitudes closer to the pole. You got the warm Atlantic water waiting for it, and it melts it away. Now, a couple of things here. They talk about, variation in large-scale ice drift. That's the Arctic Dipole that they are referencing, but I do not recall them discussing this in the paper. The Arctic Dipole, depending on the with the positioning of the highs and the lows and the calculation of the index itself, the Arctic dipole can either push ice out through the Fram Strait, for example, or the flow is such that it keeps the ice within the Arctic Ocean basin. So there's that needs to be considered. Okay, so here's the abstract, which we just went over, and I love it here. Plain language summary. This is too wonky for you. Atlantic water flows from the Nordic Seas into the Arctic Ocean, where it forms a nice warm ocean current running along the continental slope. At the beginning of this current, in the region north of Svalbard, the warm upper ocean maintains the ocean ice-free during parts of the year where sea ice otherwise would have formed. The goal of this study was to investigate whether years with a particularly large or small amount of ice in this region occur as a result of unusually high or low ocean temperatures. We examined records of temperature from instruments moored in the ocean northeast of Svalbard between 2012 and 2019. We compared these observations with satellite record of sea ice concentration along with other variables, including air temperature and sea ice movement. Our findings suggest that ocean heat strongly influences sea ice concentrations by melting ice and preventing new ice from forming, but that large year-to-year sea ice variations were not a result of variations in ocean temperatures. Instead, unusual sea ice years were associated with unusual large-scale wind patterns. Arctic dipole, which in turn control air temperature and moisture and movement of sea ice into the area from other parts of the ocean. Okay. So in the plain language summary, they basically are saying that the heat from the Atlantic water intrusion is melting the ice. But what they're saying is that we had the anomalous years, like very low ice in 2016, 2018, for example, they're saying it was not due to the warmth of the Atlantic water, but to sea ice flow patterns. Okay. That's what they're saying. So that's interesting that they're looking at they're trying to explain the anomalies is what they're basically trying to do here. And that's fine. Hey, if you need to understand why weird things happen, what causes weird things to happen. That's perfectly legitimate. They are at least acknowledging that the Atlantic water is warmer and that warm water is affecting the sea ice. We cannot lose sight of that fact that the warm water intrusion into the Arctic Ocean, not only from the Atlantic side, but from the Pacific side through the Bering Strait, is impacting sea ice, is reducing the thickness, thus the multi-year availability, is melting it earlier in the year, is preventing the freeze up that occurs normally in the oceanic fall. So the heat content of the North Atlantic, of the Atlantic water going into the Arctic Ocean is a factor. Let's not lose sight of that. Okay, so they go into a little introduction. I'll cover some of it here. Okay, the fraction of the Arctic Ocean as covered by sea ice is declining. Annual mean sea ice area in the Northern Hemisphere decreased at a rate of approximately 4.5% per decade between 1979 and 2015. And they cite Comiso et al., 2017, Struve and Notes, and Kwok in 2018. The details of the strong overall trend are complex, include spatial inhomogeneities, as well as substantial interannual variability. Of course, like everything else, you're going to have short-term variation, short-term variability, but what's the long-term trend? Okay. Many physical processes impact sea ice concentration. From here on out, it will be abbreviated SIC, and different forcing mechanisms may determine local sea ice concentration in different areas and on different temporal spatial scales, spatiotemporal variations. Local case studies important supplement to the large-scale pan-Arctic picture of sea ice evolution. Now, when we say forcing in physics, that's basically meaning something that results or creates an effect. Right? For example, Milankovitch, we have changes in the orbits forcing changes in heat distribution planet Earth's surface receives. Tilt of the axis, the shape of the orbit, precession of the solstices and equinoxes. Those are forcing that have an impact that affect the response that is seen. Areas north and northeast of Svalbard have experienced the loss of sea ice in both spring and autumn. Spring basically meaning that it's melting earlier, and autumn it's not forming up. In the 21st century, the spring ice-free area north of Svalbard has expanded eastward along the pathway of relatively warm Atlantic water. Atlantic water is transported through the eastern Fram Strait with the West Spitsbergen current, wraps around the northwestern tip of Spitsbergen, 3 separate branches, and ultimately converges along the continental margin as the warm Fram Strait branch of the Atlantic water boundary current in the Arctic Ocean. And they go on from there. And a whole bunch of citations. In contrast to most of the Arctic Ocean, where the Atlantic water is separated from the sea surface by a strong halocline layer, the Atlantic water is often bound at or in close proximity to the surface in the area north of Svalbard. Okay. Now, I just did a recent video where I went through the circulation, of currents and so on in the Arctic, and I went through some papers where I included the heat content, how many terawatts of heat was being introduced into the Arctic Ocean, and I went through all of that explaining the mechanisms as to why the ice is not forming as it did in the autumn. This ice is freezing up later in the year. In addition to open water absorbing heat energy, we have the influx of the Atlantic water. But also in the springtime, why that heat influx is melting the ice even earlier. Okay, you may want to look at that video, because from there you can see, in that video I show you the current, so you can see where the boundary current is. You can see for where the Beaufort gyre is, etc., etc. So I strongly urge you, if you have not seen that video, to do check that out. It will probably help make more sense of what's being discussed in this video here. So that was important. As a result, the region experiences large ocean atmospheric heat fluxes in autumn and winter. It is a region where variability in ocean heat content has the potential to impact the sea ice cover directly. And he cites a bunch of people, for example, Ivanov, Rapina, and Polyakov. Igor Polyakov. Igor's a friend of mine. I worked with him at IARC. He's a really cool guy, really nice guy, a very good scientist. However, it is not clear to what extent the high interannual variability in sea ice cover is a result of variable oceanic forcing. That's kind of what this study is concentrating. So again, despite what might have been said in the more technical abstract, they are acknowledging, rightly so, that the ocean heat content is impacting sea ice. It's basically causing it to freeze up later in the year and melt early in the year, thus a reduction in the sea ice cover, in the extent, in the thickness, and so forth. Interannual variations in the Arctic Ocean as a whole is primarily driven by variations in surface air temperature, SAT. Such variations are in turn governed by a complex set of drivers and interactions. Arctic surface air temperature variability is closely linked to large-scale climate modes of variability, like the Arctic oscillation. If you want to know what the Arctic oscillation is, I did a video on it. And you might, so they talk about the Arctic oscillation, but they don't talk about the Arctic dipole, which governs whether sea ice is pushed out the Fram Strait or not. So you might want to check out my Arctic oscillation and my Arctic dipole videos to learn more about that. Now, let's see, the large incidence of cyclones in the Atlantic sector of the Arctic Ocean impacts sea ice by reducing ocean atmosphere heat loss as a result of heat and moisture transport. And that's John Walsh, a very fine gentleman who I also work with. But also by increasing snowfall, mechanical fracturing sea ice by strong wind. Basically, the ice doesn't get a chance to freeze solid. It keeps being interrupted by mechanical processes, waves, winds, that kind of stuff. So it breaks it up, is what it's saying. And if you break it up, you increase the surface area, which allows for more heat absorption, which increases melting. Furthermore, variations in atmospheric circulation, that's a reference to the Arctic oscillation, can alter the spatial distribution of sea ice by impacting large-scale patterns of sea ice drift. And so we have sea ice, SIC, right? Let's go back. They defined that before as sea ice concentration. Then they also use sea ice distribution, and that will be abbreviated as SID. So SIC, sea ice concentration, SID will be sea ice distribution. So they then go on to say what the study is. Okay, they go through the data and methods. I'm not going to, if you're interested, you can click on the URL and go through that. They talk about how, all the rationale for why they chose where to put the moorings, this, that, and so on. So, and then they explain how some of the variables they were measuring or collecting. They give you some formulas here. In order to obtain approximate index of the amount of local thermodynamic ice growth, we computed the accumulation of FDD, freezing degree days, for each season. So freezing degree days is equal to the summation from your starting point minus 1.8 degrees C. That is the general freezing point for the Arctic Ocean. This is where the Arctic Ocean starts to freeze, with sea ice starts forming. And then they have minus T sub I. T sub I is the daily average 2-meter air temperature. Delta T is equal to 1 day. So I might as well just put a 1 there. And the sum is over all days within the season. And then they defined what looks like the letter H. H of X is 1 for positive, X 0 elsewhere. Sea ice drift, its SID was obtained from the NSIDC data, right, at a boulder, using satellites, etc. So again, you can read through the methodology to get the wonky details. Now we get into the results. Ice, ocean, atmosphere. Oh, they give you the breakdown. The average sea ice edge extended westward past 20 degrees east, north of Svalbard, as well as across much of the northern Barents Sea. Sea ice extent also exhibited significant interannual variability. And then they talk about August to January of 2014 stood out as a period of anomalously high sea ice concentration relative to the interannual mean. And then February to July of 2016, 2018 were enormously low, as was mentioned earlier in the abstract. SIC, sea ice concentration, right? And this is a percent here. In other words, and we can see the variability, right? You can see the variability. The gray is winter time. The white is summertime, basically. And transitionally would be fall and spring, so on. So this is the enormously high period they're talking about right here in that 2014 stretch. And then 2016 and 2018, we can see you got kind of low here, right? Look at that. It's kind of low compared to the rest of it. So that's what they're referring to there. Now, ocean temperature. Right? And again, not surprisingly, we see cyclical nature here. Okay? Different colors at different depths and so on. And again, no major surprises there, but they're showing the data. A little warming here, a little warmer than usual here, a little cooler than usual here. But otherwise, that one's kind of interesting right there. Then we have the air temperature. Again, so this is wintertime. And not surprisingly, we see a cyclical aspect to it, of course. Looks a little low there, and that's probably the lowest temperature there, and that would be going into 2019. And then we have net surface atmosphere heat flux. How much heat is going to the atmosphere? Not surprising because of the specific heat of water. If you have warm water, it's going to hold more heat. So the heat is going to go from the water to the atmosphere. That's what's being shown here. And this is where basically you start pulling heat out to freeze the water into ice. And then finally you have sea ice area flux. Again, seasonal aspect. Now, this is interesting. I'm looking at this one here and this one, and this tells me that the Arctic dipole was pushing water out the Fram Strait. Here, you see how it's a little lower? The flux is lower. That's telling me that the sea ice is being kept within the Arctic basin. And then they talk about sea ice concentration. This is starting to get into vector stuff here. There's a derivative in here. It's a little wonky for what I want to discuss here and bring with you. But again, you can go through the article. For those of you who know multivariate calculus, have at it. I do, but so it shows a bunch of nice things here. And here's a description of the figure. Time series of various variables at the shelf break. Gray background shading denotes high seasonal ice concentration seasons. Sea ice concentration in black, sea ice thickness in orange, and so on and so forth. So you see how you see the seasonal cyclical aspect to it. Some areas are going to be high, sometimes it's going to be high, sometimes it's going to be low, and they're looking at the anomalies in this study. So they give a description for the August to January 2014. The mean sea ice edge along the Atlantic water inflow pathway north of Svalbard was situated near 20 degrees east, approximately 20 degrees west of its typical location for that time period. It also extended across the northern Barents Sea. Monthly average SIC in the study region remained above 50% during the whole period, and the study site never became entirely ice-free in 2014. That was this right here. Okay, so what else do we want to? They describe ocean conditions. Average temperature were 2.48 degrees Celsius at 63 meters deep, 2.88 degrees Celsius at 107 meters deep. 2014, 2018, 2013, 2018. So you're going to say, but wait a second. How do you have warmer water deeper than the cooler water? The warmer water had a higher salinity value, makes it more dense. And I explained that in that video where I just go through Arctic Ocean circulation and the heat influxes and so forth. Temperature generally increased with depth during the season where a shallow sensor was available. Okay, that's because of the Atlantic water influence. That is measuring the influence of the Atlantic water. And okay, this is an important one to explain here. Near the seasonal temperature maximum, the potential temperature salinity, theta-S, distribution was centered within the bounds defined for Atlantic water, where, for greater than 2 degrees C, 27.7 kilograms per cubic meter. So we have a range of 27.7 to 27.97 kilograms per cubic meter. And that's the potential density. So what is meant by potential temperature, potential salinity? When you take a measurement, especially in the old days, where you sent the sample down, you collect the sample at depth. You bring it up to the surface. Well, at depth, the pressure is greater. So when pressure is greater, the molecules are pushed together closer to each other. The molecular activity, because of the increased collision, results in higher temperature. But by the time you bring that up to the surface, because the pressure is reduced, the volume tends to expand a little bit, temperature is actually lower. So you have to make a correction for that. This is why we now use the term conservative temperature when you're able to actually measure the temperature in situ based on what the pressure is, and then with the pressure, and you measure conductivity along with the temperature, you then compute the salinity, and then from the temperature and the salinity, you compute the density. So the potential temperature and salinity are basically referring to non-corrected readings until you correct them. That's basically what it is. Because that's what the potential was, but by the time we bring the sample up and measure it, it might have to change. It doesn't take much. Then these are slight changes, but it happens. Annual minimum temperature at the shelf break varies substantially between the years of the study period. Okay, and that doesn't surprise me, because you're going to have surface mixing, maybe some vertical mixing. So that is really not a very big surprise. Okay, so let's look at the temperature and surface heat fluxes. Not surprisingly, seasonality. What was found there, right? Seasonality was found. Annual mean temperatures had maxima in the low sea ice concentration years, basically absorbing heat energy, and minimums in the high sea ice concentration years. Makes perfect sense. Interannual differences were greatest in winter, and minimum monthly average air temperature was higher in the low sea ice years. Okay, here's what I wanted to discuss here. Net surface heat at the shelf break mooring location, calculated from ERA5 variables as the sum of latent and sensible heat fluxes in shortwave and longwave radiation, is shown in Figure 2D. During all years, the annual mean surface heat balance was negative, with a short summer period dominated by downward shortwave radiation, an extended winter period with heat loss from the surface to the atmosphere. Seasonal mean net upward surface heat flux was 109 watts per square meter for the August to January season of 2012 to 2018, 23 watts per square meter for the February to July season of 2013 to 2019. Heat loss was greatest over a partially or wholly ice-free ocean. The sensible and latent heat flux contributions were greatly reduced during ice-covered conditions. Okay. When sunlight energy comes in, it comes in on the shortwave part of the spectrum. It's absorbed, reflected back in the long wave. So it comes in the UV, goes out in the IR. You look at the spectrum. Okay? The sum of latent and sensible heat. In my ocean heat content video, I explained this in detail, what latent sensible heat is. Latent heat is the heat being absorbed or given off during a phase change of the material, from solid to liquid, liquid to gas, gas to liquid, liquid to solid. Okay? So if you look at the temperature graph, it increases, and you're warming up the solid, then it starts melting. Then the temperature plateaus. That's absorbing latent heat energy. Then you melt it all, and then you start warming up the liquid. You're warming it, warming it. The heat absorbed during warming of a phase, not a phase change, that's sensible heat. So if you're heating up a solid, sensible heat's being absorbed. The solid changes into a liquid, it's latent heat. You start heating the liquid, that's sensible heat. The liquid starts changing into a gas, that's latent heat. And that's energy being inputted. And then the reverse happens. When you go from a gas to a liquid, you are removing latent heat. You cool down the liquid, you're removing sensible heat. You now start freezing the liquid into a solid, removing latent heat, and then you start cooling down the solid even more, removing sensible heat. That's going on there. And they give you some, 23 watts per square meter, 109 watts per square meter. Well, have any of you ever sat under a 100-watt bulb? Kind of warm, isn't it? So imagine the energy from a 100-watt bulb warming up a square meter. It's not insignificant. And they talk about when the ocean was largely ice-free and so on and so forth. Heat loss from the largely ice-free ocean to the atmosphere was generally greatest between October and February, when upper ocean temperatures were high, decreasing from the fall maximum. Basically, the heat was diffusing into the atmosphere. That same heat that was diffusing from below to melt the ice now continues to diffuse into the atmosphere. The extended periods of low sea ice concentration during active heat loss to the atmosphere are consistent with ocean heat preventing ice formation and delaying the onset of local sea ice cover. I'm going to highlight that there for you. The extended periods of low sea ice concentration during active heat loss to the atmosphere are consistent with ocean heat preventing ice formation, delaying the onset of local sea ice cover. The implied amount of heat loss from the upper ocean is substantial. The annual heat loss to the atmosphere, integrated daily upward heat flux component from August through July, was between 2.6 and 3.5 gigajoules per square meter, like 10 to the 9th. That is substantial. That helps further warm the atmosphere. Okay, so this is also looking at the sea ice drift here. Sea ice was generally advected towards the site from the north and east, figure 1C. That's what they're talking about, from the north and east, this direction. Okay, let's see, scroll down, there we go. And some features here is Spitsbergen, Fram Strait. Here's where they played some in the morning. Here's an indication of the Atlantic water going through the, Fram Strait, FSAW, Fram Strait Atlantic water going through. So here's Spitsbergen, Novaya Zemlya, okay, Franz Josef Land, all that kind of stuff there. That's what they're talking about. Some of the locations. Now, what you see here, these little arrows, those are vectors. These are vectors of the sea ice movement. The longer the arrow, the faster the movement is. Now, I'm looking at this here, and I'm seeing ice being moved right through the Fram Strait. That tells me the Arctic Dipole is in a situation where the low pressure and the high pressure, our systems, are working in conjunction to help push the ice through Fram Strait. That's what that tells me. Sea ice advection across the transect was seasonally skewed toward the February-July season, generally is concentrated in intra-seasonal pulses near the onset of the sea ice cover period in late winter, early spring. The net flux during the August to January season had a clear maximum in 2014 about 500 square kilometers per day. This unusually large inflow of sea ice area was in part due to an unusually timed advection episode which began in July 2014 and lasted through August during what is typically the melt season. During this time, there was a strong southward sea ice drift in the western Eurasian basin of the Arctic Ocean. This is when the Arctic Dipole was most favorable for such movement. Then they go in to discuss a sea ice concentration budget, and this is the intensification factor. This is a partial derivative where sea ice denotes the sea ice, C sub I is the sea ice concentration. So you take the change in the rate of the sea ice concentration with respect to time is equal to this U that is boldface is a vector quantity, and we're dotting it with the gradient of the sea ice concentration. So this is this term here minus U sub I dotted into del. This little triangle is called del. Del C sub I minus C sub I del dot U sub I. That's the convergence. And then there's some residual here. When I did my All About Salinity video, I explained what is meant by the del operator. It's a shorthand way for looking at movement in all three directions, X, Y, Z, basically. But it's also looking at the rate of change in those directions. U is the local drift vector. R is a residual, which includes local sea ice concentration changes due to local freezing, melting, and deformation. And that's equation 2, and they evaluate it every day. Now, sea ice concentration is not a conservative property. That's an important point. Unlike sea ice mass, the flux divergence of concentration cannot be considered in balance with a single melting freezing term. Then you have errors and uncertainties, which introduce errors and uncertainties, right? So divergence is movement away from a source. Convergence is moving towards a source. So what is flux? Flux is basically a measure of a concentration of something per unit time. So for example, we could say something like a flux. If I have 3 kilograms of fish poop per cubic meter per second. So I have a concentration, the 3 kilograms of fish poop per cubic meter, right? So the amount per a given volume, and that is moving per second. Now, if I say, okay, I have the 3 kilograms of fish poop per cubic meter per second in a X direction, then I've imparted a vector, because a vector is a quantity that has magnitude and direction. If you don't specify direction, it's a scalar. So that's what flux is. It's basically a concentration per unit time movement. Now here is an interesting statement. Over seasonal timescales, the flux divergence terms, advection and convergence, were larger than the intensification. The intensification was that derivative I showed you. And by the way, that's a partial derivative, meaning that there's more than one independent variable, suggesting that the observed change in the sea ice concentration did not balance the transport of sea ice area into the region. Moreover, the net flux divergence was negative, which means positive convergence, indicating that more sea ice was advected into the region than out of it. So that's a very interesting finding. Basically, ice was gathering. Okay. So if the flux divergence is negative, that means it's converging. If it's positive, that means you have negative convergence. So convergence is accumulation, so you're concentrating it, whereas flux you're moving out of. Flux divergence, you're moving out. And again, it's still the concentration, per unit volume per time. So divergence is moving away from something. If it's negative, that means it's not moving out away from it, it's moving towards it. That's all it's saying there. Since the intensification term is negligible when summed over a long time scale, the residual term must balance total flux divergence. As a result, the residual term, which includes concentration changes due to freezing melting, is negative along an area extending from the Juramac Plateau in the west and past Franz Josef Land in the east. This trajectory corresponds approximately to the continental margin and the pathway of the Fram Strait Atlantic water, suggesting that sea ice is being lost over a region where warm Atlantic water is present. It's giving a strong correlation that heat causes the sea ice to reduce or to disappear. So they have figure 6 here, average terms of equation 2. A is a convergence, B is an advection, and C is a residual. Alternative defined such that positive values are red, indicate sea ice concentration gain. Negative values are green, indicate sea ice concentration loss. White contours are shown at intervals of 250% per year. The absolute value of the average intensification term, this partial derivative, was within plus or minus 15% per year everywhere in the domain. I wonder if I can enlarge this. Here we go. So here's convergence. Okay, see how it's concentrating? And divergence, it's moving away. Okay? And then we have the residual here. And this is the pathway, right here, this is the pathway of the Fram Strait Atlantic water. And they look at the sea ice during the past 4 decades. Sea ice concentration declined sharply during 2010-2020 relative to the 3 previous decades. This is also evident when considering the decadal mean sea ice concentration, capital M for mean, and the decadal standard deviation of annual average sea ice concentration. That's sigma, small case sigma. And figure 7 gives the sea ice concentration at the shelf break, sea ice area flux. And let's see if we can enlarge that again. And this is cubic kilometers per day. That's a volume. And looks like there's a little bit of a seasonality to it. And then it starts declining because the ice is disappearing. Remember, the green shows the ice is disappearing. And we see that here, right? 1980, 89, 90 to 99, 2000 to 2009. You see it's just getting more and more green, and it's getting even a darker green, all telling us losing the ice. Sea ice area flux into the area increased in variability and magnitude between 1980 and 2020. After 2010, positive annual sea ice concentration anomalies were preceded by intensified sea ice area export from the north. Before 2010, the interannual variability in sea ice concentration was lower and appears largely decoupled from the time series sea ice area flux, meaning it's not tied in. Okay, a little summary and discussion. Control or lack thereof of upper ocean temperature on a local SIC. The 7-year long record of upper ocean temperatures near Svalbard is dominated by strong seasonal cycle. That's expected. A seasonal cycle temperature in the Faram Strait Atlantic watercore can be explained by the advection of the seasonal temperature cycle of the Atlantic water in the Faram Strait. The increased amplitude of the seasonal cycle on the shelf break compared to the central slope suggests a broadening of the FSAW core and or a greater on-shelf transport during autumn. The on-shelf transport is a reference to Ekman pumping. Ekman pumping, if you want to know about that, I did a video called Rotating Systems. I explained it in gory detail there. It's a little lengthy to get into here. It's already a long video. The near freezing minimum temperature of 50 millimeter depth at the shelf break show that at this depth, spring temperature is more strongly influenced by surface processes than by the lateral advection of Atlantic water of varying temperatures. Now that's an interesting statement. Tells me as to where the mixing is taking place. What are the densities doing? But again, they still acknowledge the fact that the heat content of the Atlantic water does impact and affect what the sea ice is doing. But it does not, what they're saying here is does not really explain the anomalies that this study looked at. That brings us to this paragraph. A key goal of the study was to determine whether variations in local upper ocean heat content drive interannual variability in sea ice cover. The combined records of ocean temperature, satellite-derived SIC, show no evidence of such a simple relationship during the study period. Strong interannual anomalies in SIC during the study period did not correspond to abnormal temperatures in the upper ocean. Notably, there was no lack of heat available in the water column at the study during the high sea ice year of 2014, and the same was the case for the autumn autumn of 2019 up until the end of the temperature record in mid-November. Similarly, during the February to July season 2017, ocean temperatures were higher than the preceding year, yet this did not prevent sea ice concentration from remaining high for most of the period. The lack of clear covariance between ocean temperature and sea ice concentration at the study site does not, however, imply that the sea ice state is unaffected by heating from below. During extended periods in late autumn, winter, the ocean gives off heat to the atmosphere, but a persistent sea ice cover does not form. This part of the year coincides with the warm phase of the seasonal cycle in upper ocean temperatures. The combination of negative surface energy balance, diffusion upwards, and heat available in the upper ocean suggests that the warm ocean temperatures act to maintain ice-free conditions during part of the season when ice might otherwise have formed. The combined time series from the study period therefore suggests that the upper ocean heat prevented ice formation and delayed the onset of persistent sea ice cover, as well as melting the ice earlier in the year, but that large interannual variations in sea ice concentration were driven by factors other than ocean heat. So in other words, it's not just ocean heat causing melting, but other factors plays a role in the anomalies that this study was investigating. That's what's going on. So they go on to discuss further more about the sea ice drift and so on. I showed you the diagrams earlier. I mentioned the Arctic dipole. They did mention briefly the Arctic oscillation. The Arctic dipole is what drives whether sea ice goes out the Faram Straits kept in the ocean, Arctic Ocean basin. So therefore, when they talk about, well, the ice is moving in from the north, that means you have to look at what the Arctic dipole is doing. And the Arctic dipole will influence the circulatory pattern and where the ice is moved to, and therefore subjected to what they were studying here. So I would have liked to have seen them discuss the Arctic dipole in relation to that. So they go through this whole business of the sea ice concentration, I just tried to give you a background that basically you need to look at what the Arctic dipole, how that is influencing based on the air, the high and low air pressure systems, and how, as the winds move, how that pushes on the water, pushes on the ice, and affects where they flow to. Sea ice decline in the region north of Svalbard is well documented, is Igor again being cited, as well as the decrease in sea ice concentration. The region has experienced a reduction in multi-year ice. Our study suggests that sea ice drift from the north rather than variations in ocean heat content was the main driver of interannual variability of local sea ice concentration in the study region. Okay, but they're not making a blanket statement for the entire Arctic Ocean. That's what they basically just said there. They're not making a blanket statement. When you look at the overall picture, heat is what's from below and above, but the heat from the Atlantic water moving in is melting the ice from below. So it melts early in the year, and that heat persists so that the ice does not freeze up when you would expect it. It's freezing up later in the year. Thus, overall, the length of the ice season is shortening, as I showed you in that one of the figures in my ocean heat content video. The active melting sea ice also impacts the near surface layer of the ocean north of Svalbard, reducing temperature and salinity, increasing upper ocean stratification. If you get stratification, that becomes an impediment to mixing, and then that might affect what the phytoplankton are able to do. When you melt the sea ice, you're putting basically a freshwater lens. You create that halocline. Okay, and they go through a lengthy conclusion here, but basically they're going to say here what I've been saying here is that the heat from the Atlantic water is impacting the ice. They're saying that for the area of the study site that they were looking at, there are other factors impacting what the ice does. I've made the argument that it's the Arctic dipole having a strong influence. But like everything else, if you, by identifying other factors, you can improve any modeling. Like, oh, okay, we need to consider this parameter, not just this parameter. But we need to consider these others as well. But heat is the key, plain and simple. But like everything else, we live in a complex system. You have ocean interactions with the atmosphere. You have the high and low pressure systems. You've got the movement of water. You've got how the ice moves on the surface, what the currents are doing, what's the mixing, it's so on and so forth. The Arctic is changing. The Arctic sea ice is disappearing. We're headed toward the blue ocean event. When? That's open for discussion. Some are saying this year. Models I've seen indicating within a couple of years. Either way, though, losing the sea ice there, that's going to change the dynamics, not just of the Arctic, but the whole planet, because what happens in the Arctic does not stay in the Arctic. So, as I said, this is lengthy, and some people have always, I've gotten comments like, why don't you go through a scientific paper, Jim? Just actually go through it. Careful what you wish for. So, as I said, I will leave in the comments section the URL for this, so you can, because I know I kind of blasted through this, so you can read it in detail, and you can derive from it what you will, and make your own assessments and so forth. But this is a typical typical paper that we publish. So I thank you for your time and patience through this lengthy discussion. But just to reiterate, the take-home point is The Atlantic water brings heat into the Arctic Ocean. It's melting the ice earlier in the year, preventing it from freezing up later in the year. It's reducing the multi-year ice, the ice volume and thickness. But other factors may be at work when looking at local areas, such as, wind advection and so on. So in which case, then you look at what the air pressure systems are doing. And in this case here, I was mentioning the Arctic Dipole. So again, if you want to learn more about these things here, I have several videos that I recommend that I've made. One's on rotating systems, where I explain Ekman pumping and how even gyres form. Salinity, Arctic Dipole, Arctic oscillation. I did the ocean heat content video, and then as kind of a follow-up to that, I did the one on the Arctic Ocean circulation and the heat flux into it that builds up on the material I laid out in the Arctic Ocean, in the ocean heat content video. So there's a lot of other videos I've made that I hope, if you watch those, will help you understand a little better what I was trying to do here. Thank you for your time. Thank you for your patience. We'll talk soon. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.